Good evening and welcome to my channel. Today we'll be looking at connection of solar panels in parallel. Taking you through this lecture is Engineer Ibinoba Charles, lecturer, Federal University of Petroleum Resources, Efru, Delta State, Nigeria. Why parallel connection? The connection of several panels in parallel arises from the need to reach certain values of output current without changing the voltage. This simply means that if there is a system and you need a higher working hour, you need to increase your current. So in order to do that, you need to connect your panels in parallel. When connecting solar panel together in parallel, the total voltage output remains the same as it would be for a single panel, but the output current becomes the summation of the ampere rating of each panel. Thus, the effect of parallel wiring is that the voltage stays the same while the current adds up. It is important to note here that the amount of current generated by a solar panel depends on the irradiance. What is irradiance? Irradiance is the amount of solar radiation received at a given area on Earth. So as the current demand from a solar panel increases, bright sunlight is required to produce full output power. But there is a maximum limit to the amount of current a solar panel can generate, no matter how bright and intense the sunlight is. Also, if there is no load connected to a solar panel terminal, the panel will not generate current as there is no electric circuit for it to flow around. But if those two terminals, that is the positive terminal and the negative terminals, are connected together, that is they are shorted, the current demand will be very high. So the solar panel generates its maximum output current at that point when the positive and negative terminal of a solar panel is shorted, and this is usually referred to as the short circuit current of the panel on low load. How is parallel connection done? Let us see these four panels that are here. We have panel 1, panel 2, panel 3 and panel 4. To connect panels parallel, the positive of the first panel is connected to the positive of the second panel. The positive of the second panel is connected to the positive of the third panel, and the positive of the third panel is connected to the positive of the fourth panel, and the connection continues depend on the number of panels available. Also, the negative of the first panel is connected to the negative of the second panel. The negative of the second panel is connected to the negative of the third panel, and the negative of the third panel is connected to the negative of the fourth panel, and the connection continues depend on the numbers of panel available. After all this connection, the positive terminal is taken out and the negative terminal is taken out. So it is between these 2 points that all readings are taken, or connection is made to the required system. We are going to look at this our study today, connection of solar panels in parallel, under 3 different headings. Number 1, parallel connected solar panels of the same parameters. Number 2, parallel connected solar panels of different current. Number 3, parallel connected solar panels of different voltages. So we take the first case, parallel connected solar panels of the same parameters. So you can see panel 1, voltage is equals to 12 volts and the ampere is equals to 5 amp. So the total power here is 12 times 5, which is equals to 60 watts. Then we have panel 2 having the same parameter, 12 volts, 5 amps. So the total power here is 60 watts. Panel 3, 12 volts, 5 amp. So the total power here is 60 watts. So in this case, since all the panels are connected in parallel, the total voltage VT is equals to the voltage of one of the panels. So since all the panels are having the same voltage, we just take one to be our voltage. So our total voltage is equals to 12 volts. But our total current is the summation of the individual panel current. So all we need to do is to take this current 5 amps, take this current 5 amps, take this current 5 amps, and we add them together. So our total current IT is equals to 5 plus 5 plus 5, which is equals to 15 amps. And our total power PT is equals to IT times VT, which equals to 15 amps times 12 volts, which will give us 180 watts. That is our total power produced by the system, which we can also calculate. If you multiply this and this, you have 60 watts, 60 watts, 60 watts. So 60 plus 60 plus 60 is equals to 180 watts. But this only applies to systems that have the same voltage rating. So if any array consists of n numbers of solar panels with exactly the same electrical characteristics, that is, they have the same current, they have the same voltage, then the total current output is simply I times the number of panels you have in the system, and your total voltage output is equals to the voltage of one of the system. So in simple terms, instead of coming here to say I1 plus I2 plus I3, since all of them have the same current, we can well say that I total is equals to I1 times 3, because there are 3 different panels, which is 5 times 3, which will also give us 15. So as long as they have the same current rating, it is easier to just multiply one of the current rating times the number of panels you have in the parallel connection. Case Number 2, parallel connected solar panels of different current. So in this case, we can see that panel 1 have 12 volts 1 amp, making a total power of 12 watts. Panel 2 have 12 volts 5 amps, making a total power of 60 watts. Then panel 3 have 12 volts 3 amps, making a total power of 36 watts. Again, if you add all the individual power of the panel, you are going to have the total power. Or we can do it as usual, where all the panels have the same voltage. All we need to do, the total voltage is equals to the voltage of one of the panel. So simply, our voltage is equals to 12 volts. And our total current, IT, is equals to the summation of the individual solar panel. Like in the first case, all the currents were the same. So it is easier in that case to pick one of the panel current and multiply by the total number of panels in the system. But in cases where the panels current are not the same, all we need to do is to add each of the solar panel current together to get the total current. So in this case, we say 1 amps plus 5 amps plus 3 amps, which is 1 amp plus 5 amps plus 3 amps. This will give us 9 amps. Our total power again, P total is equals to I total times V total, which is equals to 9 times 12. And this is going to give us 108 watts. It is very important to note here that when panels are manufactured, manufacturer usually put on the nameplate the power of the panel. Some are rated 100 watts, 150 watts, and so on and so forth. These power are usually abbreviated at the back of the panel as WP, which means watts power. This wattage value is where the normal voltage and current rating of the panel apply on the current and voltage characteristics curve. That is the IV curve. For example, if we have a panel rated 12 volts 5 amps, our total power is simply IV, which is equals to 5 times 12, which is equals to 60 watts. However, the short circuit current, which is usually refers to ISC, is the panel current measured at full irradiance, which is about 1000 watts per meter square. When the positive and negative terminal are shorted, this short circuit current is the maximum current that a panel is capable of producing when the voltage across it is 0. That is to say, when there is no load connected to the system. That is, your V is equals to 0. A panel's short circuit current depends on a number of factors. One of them include the area of the solar panel, the irradiance, and also the temperature. But a panel's short circuit current can be as much as 10% higher than the panel nominal current rating. That is what we refer to as, at the back of the panel, you will see IMP. That is the normal rating of the panel. While the short circuit panel can be as 10% higher than the panel normal current rating, IMP, which may not sound very much but could result in excess overcurrent through cable for large parallel connection of panel. While our simple example has a nominal current of 9 amps as we see here, at maximum power it could potentially be higher at 9.9 amps, that is 9 amps times 1.1, which is equals to 9.9 amps. It is this higher current value which needs to be considered when installing cable between parallel connected panels and DC load, so that there will not be burn in the system. So after calculating your current of the panel using the nominal value, it is very important to multiply it by 1.1 so that you will use that value in order to do your cable sizing. Case number 3, parallel connected solar panels of different voltages. So we can see here that this panel, first panel is rated 8 volts 5 amps, second panel is rated 12 volts 5 amps, and the third panel is rated 18 volts 5 amps. You may want to go with the assumption that if you multiply this voltage and current, you have your total power of 40 watts. If you multiply this current and voltage, you get a total power of 60 watts. And if you multiply this current and voltage, you have a total power of 90 watts. Just as is shown here, 8 times 5 40, second panel 12 times 5 60, and third panel 18 times 5 90. So your total power for this your assumptions is 90 watts. Now let us look at it from the other perspective, where we need to consider the current rating by adding it together and picking our voltage. So looking at it from that aspect, we add all the individual panel current together as usual. So we have 5 amps plus 5 amps plus 5 amps equals to 15 amps. Whether they are different or they are the same current, we add them together. But in this case, we cannot take the panel with the highest voltage. The output voltage of this particular system will be limited to the value of the lowest panel, that is the voltage of the lower panel in the parallel connection, which is 8 volts, due to this voltage mismatch. So you can see, so if we apply that law, we notice that our total voltage will now be equals to 8 volts. So by the time we multiply that our current times our voltage, we see that our total power for this actual system is 120 watts, which is the correct answer. So it is clear that your assumption is wrong, because the power available to the connected load is only 120 watts, clearly reducing the PV panel actual wattage to about 63% of the maximum, like what we calculated here before, 190 watts during our assumption. You can see that the actual power is 120. That means it has been reduced to 63%. So in this case, you will discover that a lot of money have been wasted on the purchase of higher wattage of panel when they are actually not doing anything in the system. However, At lower output voltage, this mismatch may not be a problem, but as the solar irradiance increases towards full sunlight, that is 1000 watts per meter, the mismatch in the current voltage characteristics curve of each photovoltaic panel can cause a significant power loss in a large array. So, in any parallel installation, it is very important to avoid any form of panel characteristic mismatch. In conclusion, to achieve maximum power output, before connecting panels in parallel, they must meet the following condition. Number one, have the same voltage and current. Number two, have the same voltage and different current. So the emphasis here is the same voltage. Before connecting panels in parallel, ensure that all the voltages of the individual panels are the same. Otherwise, if any one is different in the entire system, it is the panel with the smaller voltage that is used in the calculation, and this will result in a large power loss in the entire system. So you can try this and leave your answer in the comment section. 3 solar panels of 13 amps 78 watts, 12 amps 96 watts, and 12 amps 120 watts are connected in parallel. What is the total power output of the arrangement? If you find this lecture very interesting, I want you to like this video, share it with friends and colleagues, subscribe to my channel for more interesting lecture series on different areas. Thanks for watching.